What is the biggest perfect symmetric shape you can think of? You may already know Platonic solids, convex shapes made from identical polygons, perfectly regular and highly symmetric. But once we allow different kinds of faces, an entirely new zoo of symmetric solids appears. So the question is simple to ask. Which symmetric solid has the most vertices, edges, and faces? In 3 dimensions, the largest symmetric polyhedron already looks overwhelming. It's packed with faces, edges, and vertices. But in the end, it's still recognizably solid and almost familiar, just a cube taken to the extreme. But step into 4 dimensions and things get completely insane. The number of possible shapes explodes. Structure turns into excess, symmetry into extravagance. What was complicated in 3 dimensions becomes almost incomprehensible in 4. And yet, these higher dimensional giants are real mathematical objects. With the right perspective, we can visualize them, unfold them, and even take them apart piece by piece. So join me on a slightly crazy journey to the largest symmetric shapes that Euclidean geometry allows, and prepare to stretch your imagination far beyond your usual limits. We will start slowly by looking at the Platonic solids made entirely out of triangles. We have 3 options. At one vertex, 3, 4, or 5 triangles can be arranged. 3 triangles leave a gap of 180 degrees. In the case of 4 triangles, at one vertex, the gap is reduced to 120 degrees. Finally, 5 triangles at one vertex only leave a gap of 60 degrees. When the big gap of 180 degrees is closed through folding, a tiny tetrahedron is formed that can be completed with one additional triangle. The folding of the gap that is left by 4 triangles leads to a somewhat larger octahedron. 4 more triangles are needed to finish this shape completely. In the final case, the 5 triangles fold into the start of an icosahedron that requires 20 triangles in total. We can conclude that the size of the gap determines the size of the resulting polyhedron. How can we find the smallest possible gap? Let's have a closer look at the geometry of regular polygons. A polygon can be divided into congruent triangles, similar to a cake that is cut into pieces. These triangular pieces are isosceles. The angle alpha at the tip is 360 degrees divided by the number of sides. The total angle sum inside a triangle, 180 degrees reduced by alpha, is distributed evenly between the 2 angles beta at the base. The internal angle of the polygon is 2 times beta and therefore given by 180 degrees minus 360 over n. This table summarizes the internal angles for the different kinds of polygons. With this table, we can search for combinations of polygons whose sum of internal angles is as close to 360 degrees as possible. The most exciting combinations of polygons includes one square, one hexagon, and one decagon, a polygon with 10 vertices. The total sum is only short by 6 degrees. Let's have a look at what a shape can be built from such a vertex arrangement. We end up with a truncated Icosidodecahedron that consists of 12 decagons, 20 hexagons, and 30 squares. The total number of vertices is 120. Having built this largest 3-dimensional polyhedron, I want to take you on a little side trip. This solid, apart from its ridiculously long name, has a very concise and more abstract notation. It is denoted by the following Coxeter-Dynkin diagram. Each dot represents a plane of reflection. Planes of unconnected dots are orthogonal. Dots connected by a line with a 3 on top, which is usually omitted, subtend an angle of pi over 3 or 60 degrees, and planes with an angle of pi over 5 or 36 degrees are denoted with a line with a 5 on top. Now all the dots carry rings, which indicate that the initial vertex that creates this polyhedron by repeated reflections on those mirrors sits right in the middle of all three planes. It is represented by the yellow sphere. When one ring is omitted, this mirror becomes inactive for the initial vertex, and the resulting polyhedron is losing half of its vertices and a few edges and faces. By just removing rings from the dots and deactivating mirror planes, all small polyhedra with this mirror symmetry can be constructed. Suddenly, these solids are much more than just a random arrangement of edges and vertices. They are manifestations of reflection symmetries. In 3 dimensions, there are alternative ways to arrange mirrors for non-trivial polyhedra. The next arrangement produces a truncated cube octahedron. Deactivating mirrors leads to more of the polyhedra we've seen before. Finally, the most symmetric arrangement of mirrors leads to the truncated octahedron and a few other siblings. We finish this side trip with the remark that there are infinitely many other arrangements of mirrors, which are less spectacular, however, since they only lead to prisms with any number of faces you can think of. It's not a waste of energy to keep the collection of these polyhedra in mind. They all can be used as building blocks for polytopes in 4 dimensions. However, before we actively construct these 4-dimensional solids, we have to add one additional tool for the exploration. Shortly, we will construct 4-dimensional solids from 3-dimensional polyhedra. However, the lack of intuition makes it difficult to understand how many polyhedra are needed to complete the construction. Stereographic projection will come to the rescue. Let's understand its action in 3 dimensions first. Imagine we want to build a dodecahedron. We start with a single pentagon. This pentagon has 5 edges to be paired. Naturally, we place one more pentagon at each edge. From our folding experience, we see that neighboring edges are paired. The small gap will vanish after folding, but now we are left with 10 unpaired edges. The next layer of pentagons will always pair the directly adjacent edge and another edge separated by a larger gap. You can see that after 5 additional pentagons, only 5 edges are left unpaired. These edges are paired with the last pentagon that completes the net. You certainly agree that this process is cumbersome. In 4 dimensions, we would have to pair faces instead of edges. Let's see how this process simplifies with stereographic projection. To quickly remind you of the process, let's take a look at this image of a shiny dodecahedron. We imagine a plane of projection that cuts right through the middle. All the vertices of the dodecahedron are located on a sphere indicated by the green grid lines. From the north pole of that sphere, we send rays in direction of every vertex. If a ray hits a vertex, we assume that it goes right through it. All we care about is where those rays hit the plane of projection. This will become the position of the projected vertex. When the new vertices of the projection are connected by edges, the 2-dimensional projection of the dodecahedron is complete. Of course, this projection is sensitive to the orientation of the dodecahedron. But most importantly, it shows a 2-dimensional representation of the original dodecahedron that preserves its structure. Let's collect the 3 different ways of representing polyhedra in one slide. We have the familiar 3-dimensional representation that we can hold in our hand and play with. Then there is the corresponding net that we can cut out and fold into the 3-dimensional solid. And finally, there is the stereographic projection. For the truncated Icosidodecahedron, the largest 3-dimensional polyhedron, we find a similar picture. Please note how the number of polygons in each layer increases until we have built the solid halfway through. Then it reduces again, and we know that we are done when the stereographic projection takes the shape of the last face. This is much easier than identifying edges. Luckily, the second and third representation survive when we step to 4 dimensions. Then it takes 3 dimensions to show the net and a stereographic projection. The largest polytope in 4 dimensions goes by the following Coxeter-Dynkin diagram. Paul Dirac once said that his equation was smarter than him after he had discovered the antiparticle of the electron hiding inside his famous equation. These Coxeter-Dynkin diagrams similarly are much more powerful than you might expect at first sight. For instance, if you want to know what the 3-dimensional boundary of this 4-dimensional shape looks like, all you have to do is remove a dot and its connecting edges from the diagram. There are 4 possibilities to remove a dot, therefore there are 4 different boundary shapes. At each vertex, the following 4 polyhedra meet: a truncated Icosidodecahedron, a 10-prism, a 6-prism, and a truncated octahedron. Do they fit together at all? Let's have a closer look. We start with the largest solid, the truncated Icosidodecahedron. At one of its decagons, we attach a 10-prism. Right next to it, the truncated octahedron is placed, such that a square is facing the 10-prism. Finally, a 6-prism has to be squeezed into the remaining location at the common vertex. Can you spot the tiny gaps between these polyhedra? More than 99% of the available solid angle is filled. These gaps will be closed when folded into a 4th dimension. Do you have any idea how many polyhedra are needed to complete this construction? Without further ado, let me show you the result. To distract you a little bit from this unfolding beauty, let's crunch some numbers. There will be 120 truncated Icosidodecahedra with 120 vertices each. There will be 600 truncated octahedra with 24 vertices each, 720 10-prisms with 20 vertices, and 1206 prisms with 12 vertices. You can see that the product of these numbers in each line always gives 14,400, the total number of vertices which are evenly shared among all the boundary cells. When folded, the solid will consist of 4,800 hexagons, 1,440 decagons, and 10,800 squares, adding to a total of 17,040 polygons. The statistics are completed by 28,800 edges. When we alternatingly subtract and add these counts for the objects in different dimensions, so to speak, 14,400 vertices minus 28,800 edges plus 17,040 polygons minus 2,640 polyhedra, we get 0. This is the Euler number in 4 dimensions. Every polytope with no holes satisfies this constraint. In this animation, 10 pieces are placed every second. At this rate, it will take about 4 minutes to complete the construction. I was tempted to speed it up during the making of the video, but well, on the other hand, time is maybe the only way how we can sense the complexity of this construction. This complexity is in sharp contrast to the production of this object in the 3D renderer. You might think that it took forever to assemble all the pieces and put them into the right position with the right orientation. But of course, everything was established through computation, and it didn't even require calculus. It was all just linear algebra. The starting point is one single point in 4-dimensional space, and 4 mirrors of reflection. The action of reflection is simulated by simple matrix multiplication. These 4 matrices generate 14,400 different points in the 4-dimensional space when applied repeatedly. And these 14,400 points are the vertices of the net that grows in front of your eyes. The second part is working out the structure of the edges, polygons, and polyhedra at one single vertex. The edges are just the connections to the nearest neighbors. For faces and polyhedra, you have to construct all possible equations for planes and hyperplanes, most easily done by computing normals. Once you have found the vertices, edges, and faces of the truncated Icosidodecahedron, of the truncated octahedron, of the 10 prism and the 6 prism, you can again use the mirror matrices to teleport them into the remaining shapes. By the way, all these computations are best performed to infinite precision. It's a fun exercise to only work with fractions and the square root of 5 symbolically. In Python, you can nicely override operators for addition, subtraction, multiplication, and division to achieve this goal. In a third step, you have to unfold the polytope into a three-dimensional net. This might look scary, and indeed it took a while to work it out. But since every polyhedron is defined by its normal, you basically only have to rotate them such that all normals eventually point in the same direction. But when you rotate a polyhedron close to the root of your net, you have to simultaneously rotate all its children. A fun fact also, this rotation does not fix an edge as it does in 3 dimensions. It fixes an entire face. But after all these rotations are just matrix multiplications and appropriate translations. This is, of course, just a 4-minute teaser that describes the efforts of weeks or even months. If you feel the urge to do it yourself, you should give it a try. You can always start in 3 dimensions and unfold a tetrahedron or an icosahedron. And if you get stuck, don't hesitate to leave questions in the comments. You can find the code on my GitHub repository, but maybe it is easier to write your own code and learn beautiful math along the way than trying to understand what I wrote. Next, we show 2 runs of stereographic projections, one without the truncated octahedra and one without the truncated Icosidodecahedra. And remember, what you see is the projection of the vertices that live on a 4-dimensional sphere. The light rays from the north pole of the sphere project them onto a 3-dimensional plane of projection, which is our 3-dimensional space that you are exploring on your 2-dimensional screen. I hope that you are kind of amazed and shocked at the same time. These solids really go crazy in 4 dimensions. I haven't emphasized it, but you've probably realized that the largest 3-dimensional solid, the truncated Icosidodecahedron, was a building block of the largest 4-dimensional solid. You might wonder whether this 4-dimensional solid is the building block of a 5-dimensional, largest, even more crazy polytope. At this point, there is some disappointment. A similar arrangement of mirrors in 5 dimensions will not lead to a finite number of reflection images, and does not lead to a 5-dimensional polytope. Nevertheless, other arrangements of mirrors continue to exist in higher dimensions, and the complexity continues to increase. Do you have any idea what's waiting for you in 8 dimensions? There you have objects with millions of vertices, but that's for another day. If you liked this video, stay tuned for the next one. Hope to see you again. Bye bye.